Recording in progress.
All right, everybody. Nice to see you, or have you here at least. Let's talk about CS theory. Does anybody have any questions?
I had a question about 2D.
2D, let's see, what is 2D? This time I came prepared with the homework right here. Maybe I can even draw on it. Like, oh yeah, 2D, check it out. Oh yeah, this is the like trickiest possible question. Not possible question, I think it's maybe like a tricky question. This is asking us to explain why the constant, this magic constant in Stirling's formula is square root 2 pi. And like somehow the truth of the matter is it like comes out of the fact that, you know, if you flip a bunch of coin flips, it looks like a Gaussian, and Gaussian has like some square root 2s and square root pi's in it. But nailing it down is not super easy. And I suggested you do it by invoking this powerful theorem that gives you the central limit theorem with error bounds, Esseen theorem. So it's still tricky though. So yeah, what's the question? What's on your mind?
I guess I'm thinking about how to interpret the hint. So what our group has been like doing so far is like comparing the probability that you get like at most or the probability that you get like at least n over 2 heads with the probability that you get like at least n over 2 plus k. Like we assumed that k was like one standard deviation out.
Okay.
And we tried the computation.
Okay.
And tried to see what would happen. And we also, I guess like something else is, we tried using like the central binomial coefficient as like an approximation for this. Like it'll give you, I guess, if you like subtract these, the central binomial coefficient can give you like a lower bound and maybe an upper bound. If you like do stuff.
Okay.
And I guess like another thing is like, I guess we noticed that like if you plug in like the supposed form of like the of like n factorial in like the previous problem into like the central binomial coefficient, it's like rather nice. Like some things cancel out.
Okay.
Yeah. So I guess.
Go ahead.
We've been trying to like connect the dots from there.
Okay. Well, let's set some things up. I mean, what do you want to get into first? Like the binomial coefficients and the factorials, or like the probabilities of certain numbers of heads, or what?
I guess it's more of like the very essence side. Like, how do you approximate this using that theorem?
Okay. Let's have a random variable. What should we make the random variable be?
I guess just like the sum of the coin flips.
Oh, okay.
Like maybe
so
normalized.
Yeah. So normalized or not normalized?
I guess like we computed something like this like in class.
Okay.
I guess what was the result? I think the result was like if you like flip n coins, then like the probability that like the number of heads is less than or equal to n over 2 plus like some standard deviations like multiplied by square root n over 2.
Right.
So like
plus, let's say, t standard deviations, and the standard deviation for the number of heads is root n over 2. Yeah.
And that's like approximately like the standard normal CDF plus or minus like 0.56 over root n.
Yeah. Let's see, plus or minus some constant. I'll just write it as c over root n. This is how I would like to write it too. I mean, like theoretically, you should say like blah minus blah in absolute value is at most c over root n, but I just like this slightly wrong notation of plus or minus c root n as well. Yeah, true. Okay, good. So yeah, should we apply this somehow? Yeah, let's actually just draw like a little picture too to remind ourselves. Like this is the Gaussian PDF. Such a great bell curve. It's like phi of t. Yeah, and so if like, I don't know, t is something, if this, for example, is t, then this blue stuff is phi of t. Okay, so did you want to like apply this for some values of t or?
Yeah, so I guess like if we're subtracting the two probabilities, that
Okay, oh, you want to subtract this one and this one?
yeah,
Okay, so let's see. So this first one, well, we put greater than or equal to here. I don't know, should we put, that's fine. Okay, so that is like, yeah, I should say, by the way, that like, okay, this is like Gaussian land. And then like, if you actually like, flip the coins and like, did like a little histogram of the probability of getting like each exact value, let's assume that n is, well, I guess you would get like some situation here where like this is like n/2, and like you get some height here. This would somehow be proportional to like 1/√n, I guess. And then you get this like kind of discrete thing that sort of looks like a bell curve as well. Like it would start to like maybe tend down to, you know, looking close to 0 or looking a lot smaller in the range of √n, but like somehow these pictures are supposed to be similar. Okay, so let's see. So like, I'm just trying to like, it's not easy for you to like write on my screen. So I'll try to write like maybe what you might write. Let's call this 1, and we'll come back to 2. So you're saying like, okay, for 1, this is kind of like taking, okay, in here, let's call this 1 star. This is kind of like taking t equals 0 in star, right? Well, one on the hand, we have greater than that. Let's put less than here, just because we had less than in star. Okay, so I guess what that's saying is like probability that like the number of heads is less than n/2. I guess Barry Esseen tells us that like this is approximately phi of 0 plus or minus some constant over √n. And I guess phi of 0 we know, right? Phi of 0 is, does somebody want to say?
like just a half.
Yeah, it's a half. Okay, plus or minus c over √n. I guess we didn't really need Barry Esseen for this, right? Because like the probability of the number of heads being less than or equal to n/2. Okay, actually maybe we kind of, well, okay. If n were odd, then it would be, n/2 would not be an integer and be right in the middle. So it'd be literally exactly half the probability. This would be literally exactly half if n is odd. If n is even, then I guess like it's like a little bit bigger than a half because like n/2 is an integer and I wrote less than or equal to here. And so I guess this also sort of tells you like that, well, the probability of it being exactly n/2 is probably on the order of constant over √n, like if Barry Esseen is true, because Barry Esseen is going to tell you like it's a half plus or minus like c over √n, and like this error can only be coming from the probability of exactly hitting n/2. I guess we already knew that when we studied the central binomial coefficient. Okay. So okay, so then you're saying like in 2, well, let's like make this like, did you have like some value in mind for like here?
We were just using like 1 standard deviation.
Okay.
So I guess like √n/2.
Okay, so like √n/2. Okay, so then in 2, it's like t equals 1. So you get that the probability that the number of heads is less than or equal to n/2 plus √n/2 is like phi of 1 plus or minus c over √n. Phi of 1 is like, well, it's a number, right? I don't know what it is. It's the probability of all this stuff in here. It's like 60, I don't know if it's like 67% or 73% or something. I don't know if you happen to know. Let's just invent a number. It's probably not right, but like, let's say it's 70.73. I just made that up, plus or minus c over root n. So we could subtract. And then on the one hand, we'd have the probability that like the number of heads is, let's see, the opposite of this condition is like that you're bigger than n over 2, number of heads. And that's n over 2 plus root n over 2. And then if we subtract these things, we get, well, this fictional number, 0.23. And then we should still say like plus or minus like maybe like 2c over root n, because we're not being very careful about what way the errors are going. So maybe they could add up unfavorably, but this probably won't really matter that much. Okay, so this is nice. So this is like telling us that if you look at this like discrete picture over 2, and you like add up literally all the heights of these bars, add up literally all the heights of these bars, you know, these bars are supposed to be like the probability of getting each individual number in the actual coin flipping experiment. And this adds up to basically 0.23, or whatever that specific number is, you know, plus or minus like 1 over root n. Okay, all good deductions. And indeed, this is how you typically use vary Esseen to do stuff. But now, okay, somehow Stirling's formula has to get into the picture, right? That's what this problem's about.
Yeah, like I guess it's kind of annoying that when you subtract, you get this like 0.23 thing instead of like something related to like root 2 pi.
Yeah. So where's the root 2 pi gonna come in this picture?
I guess, I mean, it's like the top of the curve on the Gaussian side, right?
Yeah, that's right. This thing, this height right here is, I don't know, I shouldn't have done that in green. Let's try sparkle color. This height right here, okay, sparkle color is no good. This is 1 over root 2 pi. Okay, so that's a good clue. Like that's coming in there. So, okay, good. So how can this help us?
I guess one idea that may or may not work is like you could like upper bound the difference of like the CDFs by like taking the rectangle instead.
Yeah, that's true. So yeah, so actually what we did here, we kind of like said like this. Okay, so actually this amount here was like this, you know, fictional number 0.23. Well, whatever it really is. This is 0, this is 1. And you're right, it does. I mean, you could say that like, oh, it's sort of related to this rectangle has height 1 over root 2 pi and width 1. So we know that 0.23 is at most this. Yeah, I don't know if it is. What is 1 over root 2 pi? 1 over square root 6. Well, anyway, yeah. But I guess like the point is that like, okay, this blue curvy trapezoid or whatever, it's kind of looks like the rectangle. So it kind of looks like 1 over root 2 pi, but like there's a pretty chunky error here. So it's not exactly great. And by the way, like anybody else who's on the call here can also chip in. This doesn't have to be like a one-on-one thing. Yeah, any thoughts about that? No? No thoughts?
I guess like another thing we were thinking about is like the complement of the CDF. So like
Mm-hmm.
the other tail.
Mm-hmm.
I think we showed in class that it's like asymptotically like proportional to like the PDF, which involves like the root 2 pi thing. So like,
True.
I don't know, maybe like set k to be maybe set like t to be like a larger value so that you can like use that.
Yeah, that's a creative idea. You're saying that like if t is like quite big, you look at like this probability, we show that this is like phi bar t. We show that's like asymptotic to phi of t, which we know is like this, it's got a root 2 pi in it too. This is like to minus t squared over 2. Possible. This is a good idea. You gotta get the factorials involved somewhere too. Yeah. Okay, let's hypothetically put a pin in this one. We'll come back to it later in this recitation. But let's just pause for now, and maybe inspiration will strike us. We'll come back to it for a moment. Yeah. Okay. Given that we've paused, is there another question? Oh, we got all these like friendly faces here. Maybe I should just call on somebody and say, how's the homework going for you? Did y'all like solve everything? All right, I'll ask somebody, I'll pick at random here. We got 7 people. I'm picking a number between 1 and 7 in my head. Okay. Oh, it came out to SG. Oh, you were asking some questions on Piazza, in fact, I think. How's the homework going for you?
It's funny. I think someone just left right before you randomly called.
Oh.
It's going all right. I was also working on 2.
Okay.
C and D. So that was helpful.
Yeah, all right.
I guess I haven't spent that much time on 2.3, but we could look at 2.3 as well. The integral
Sure.
is pretty confusing for me.
Okay. Yeah, let's take a look at problem 2.3 for a moment, and then we'll return to 2.2D. Okay, one thing is like, okay, so this is about some formula. So our expectations of things. Let's focus on like the k equals 1 as it said here. So okay, so this is like, it's like a pretty relatively well-used formula in life. So let's plug in k to be 1. So we're interested in this expectation of x is, okay, k is 1, so it's integral from 0 to infinity. Looks mildly intimidating there. And then t to the k minus 1, that's just 1. So we can ignore it. And then probability that x is greater than or equal to t dt. Okay, so this is what we're supposed to prove. Let's just do an example. That way we'll maybe be less, I don't know, it looks intimidating, so less intimidating. Let's have a random variable. Let's pick our favorite. Well, let's pick a random variable that's like not too complicated, but like not too simple either. So like say x is oh, it's supposed to be non-negative too. So okay, so only give me some non-negative values. So like let's say some value with probability something, some value with probability something. Okay, somebody give me a value for this. If you're on the call.
Is 1 and 0 too simple? Probably.
Pretty simple. Well, let's go for 1 though. That's good. Okay, so 1 with probability. What should we give it?
2/3.
2/3. Okay. Let's have 3 values. Okay. So let's have another value here.
5.
Thank you. 5. Great. 5. Oh, color code it. Okay. And what probability should 5 have? We have 1/3 left. But don't make it 1/3. Come on, we just need to pick a number.
1/6.
1/6. Okay. Oh, now we have 1/6 left. Very symmetric. Let's round this down to let's make this 0.7. We'll round this up to 0.2. So that leaves us with 0.1. Okay, we need one more value here.
Can I say something non-integer?
Yeah, please. But don't make it like super. Well, go ahead.
8.2.
8.2. I love it. Okay, great. What a wonderful random variable. I'm loving it. This is great. Okay, 8.2. So first up, I can do this now. Okay, here we go. I'm going to calculate the expectation. Expectation of x. I'm going to calculate the left side and the right side, and like hopefully they'll be the same. The expectation of x, I can do this. It's 0.7 times 1 plus 0.2. Okay, we're scratching these out. Times 5. Oh, that's going to be nice. Plus 0.1 times 8.2. Oh, I can do this. This is 0.7. This is literally 1. And this is 0.82. So we get 2.52. Oh, great. That turned out great. I'm loving this question so far. Okay, so now we got to do this thing. Okay. So you see, this is weirdly, okay, we're integrating. We have something that looks like this, right? Integral of blah dt. So hopefully this should be like a function of t. So it like matches up with our expectations for how functions work. And I guess it is, right? Like for every value of t, this is some number. So like, okay, I'll ask you a question now. If this is our x, let's pick a nice value of t, like 4. So what is probability that x is greater than or equal to? In fact, let's call this f of t. So let me ask you now, what is f of 4?
0.3.
0.3, yep, because these are the two cases where you're bigger than 4, so it's like 0.3. And let's do some more, like f of 0, just shout it out.
1.
1. F of a half.
1.
Still 1. F of, okay, it's a bit annoying. So let me say like f of 1.1.
0.3.
Yeah, f of, okay, I'll do a couple more. 3.
0.3.
Yeah, f of 6.
0.1.
Yeah, f of 10.
0.
Okay, great. So we got a lot of things. Hopefully you get the gist of it. So now let's plot f. Here's t. Here's, oh, this is the plot of f. T. Okay, so it starts out at 0, it's 1. And then I guess it's like 1 for a while. This is 1, and it goes 1. Okay, all this is like the cutoff point. So then it jumps down somewhere in the neighborhood of 1. It jumps down to like 0.3. This is like 0.3. And then it goes 0.3 for a while. And then somewhere in the neighborhood of, I guess, 5, just way out here, jumps down to 0.1. 0.1. And then somewhere in the neighborhood of 8.2, okay, it jumps down to 0. So let's finish this picture. Here's 8.2. It jumps down to 0. Okay, so this is like, not like the most common function you see in calculus because it's like discontinuous, but that's fine. And then, okay, so that's f of t. And then finally, we're doing integral 0 to infinity of f of t dt. Okay, that's the area under this curve. So that we can do. I'll take over this part. It's like the volume, or sorry, the area of all these rectangles. Well, there's nothing under the curve there. Okay, so this was a rectangle with width 1 and height 1. And this one is a rectangle with width 4 and height 0.3. And this one is a rectangle with width 3.2 and height 0.1. Okay, so now we have to add this up. I can do that. 1 plus 1.2 plus 0.32, which adds up to 2.52. Oh, thank God. All right, it's a miracle. These two things are equal. Okay, so it's funny though, because like, we added up three like quite different looking numbers here and three quite different looking numbers here, and we got the same result like both times. So that's neat. Yeah. Any comments on that or thoughts? How did it happen?
I guess you can cut it like horizontally and vertically, and that's like how you get the two different kinds of sums.
Yeah, that's true. That's right. This is a classic way to prove this. It's exactly right. You can be all sneaky and be like, oh, see this area under the curve that we computed, I could do the rectangles this way. It's like this rectangle, Mr. Yellow, plus this like blue, Ms. Blue over here, and like red over here. Yeah, and if you compute it this way, see this one, the height is 0.7 and well, wait a minute. Yeah, the height is 0.7 and the width is 1. And then the blue, the height is 0.3 minus 0.1, which is 0.2 times the width is 5. And then the yellow guy is the height is 0.1 and the width is 8.2. Aha, right? You see in this calculation is the same as this. Okay, very good. So in light of that, you might say like, okay, this one's not the coincidence. So probably you could take that and run with it and prove the result in the k equals 1 case. Actually, as I said, this k equals 1 case is the case that's by far most commonly used. Actually, why is that? Like, what's the whole point of this stupid formula? The whole point of this stupid formula is like sometimes in life, okay, usually if you have a random variable in life, usually figuring out like expectation of x is not so bad. And like figuring out like this is pretty good. And figuring out the probability that x is bigger than t, this is like pretty not so great. This is what we've been talking about for a while. Like when we saw like Chernoff bounds, we were like, oh, x is like a sum of a bunch of coin flips. Understanding of its expectation, piece of cake, no problem. But understanding like the probability, it's like bigger than t. This was hard. We needed Chernoff bounds. We did approximations, and that's the general way of the world. But sometimes it can happen that the reverse is true. Like not always, but sometimes. Well, maybe I'll try to give an example. But sometimes in life, like weirdly, like you're kind of know some stuff about this one, and you, for whatever reason, don't know about this one. And you're like, oh, weirdly, I have this information. I wish I had this information. And you can get it by this formula. Like if you knew this like perfectly for every value of t, then you'd be like, oh, I could just integrate it and I'll learn the expectation. And like occasionally that like actually happens. I can even like give it like an example, which may be relevant because maybe there'll be another homework problem in which you'll be asked to use this homework problem later. So if you're watching this, you may have like a leg up potentially. What if I like asked you to compute the expected number of heads in n coin flips, but like times the indicator that the number of heads is at least n over 2 plus, I don't know, root n or something. So in other words, like, I want you to calculate the, flip a coin like n times, but instead of like taking that, like only take the number of heads if it's at least n over 2 plus root n, and otherwise take 0. So that's like a slightly odd thing to do, but like it comes up. Like maybe you're somehow interested in like what's the expected number of heads, like given that the number of heads was like at least 2 standard deviations above its mean. We call this random variable x. Then it's not so easy to figure out like what is that expectation of x. It's not super clear. But probability that like x is greater than or equal to t, you have some like decent information about, because if t is less than n over 2 plus root n, then this probability is 0. Well, maybe we should put like greater than here. Because x is 0 if the number of heads was less than n over 2 plus root n. And otherwise, if t is bigger than this amount, then we have like the probability that the number of coin flips is bigger than some number, and we could use like Berry Esseen for that. So it's like a situation where like you might actually be able to reasonably estimate this, and like this is the hard thing to figure out. Okay, so that was like some weird digression about why you might be interested in this formula. Also, if we return to this formula, like it's sometimes I've seen it called the layer cake formula. So if you ever see this like in life, the layer cake formula, it's referring to this thing. And I guess it's somehow like this picture kind of looks like a layer cake. Maybe like this is supposed to be like, you're seeing like a cake in profile, and like, yeah, like maybe you made the top layer with some delicious like red velvet cake, and then the second part was like some blueberry, and you had like a lemon cake on the bottom. And yeah, you can compute the amount of delicious cake you have in 2 different ways. Yeah, but this, okay. So this was all about the case of k equals 1. K equals 2 is a little bit more interesting. But probably if you just like literally repeat this exercise exactly with k equals 2, and you're like, okay, now we're computing the expected value of x squared. So you're gonna be like, all right, I'm gonna have to like put like a square here and a square here and a square here. And I don't know, do this calculation. And then like this integral, apparently we got to like stick a 2 out here. And we also have to stick like a times t in here. It's going to be kind of funkier. But perhaps if we do that calculation, we will become enlightened. Neither of these things is actually like looking at there's sort of like a hint, but well, anyway, this would be like, I mean, especially if I didn't have a hint, like this would be my natural inclination. I'd be like, all right, well, let's just try it out with k equals 2 and see why it could be true. But well, let's put a pin in that one too. Like maybe it's time we can come back to that one as well.
One quick question about the hint, just like, so it's saying to interchange the sum. Well, I think it's like an integral is like morally the same thing as the sum. I was just wondering, like, if we know we are allowed to interchange the integral and the sum. I actually didn't know whether.
Good question. Okay, yeah, that's a little bit okay. Good point. So, all right, in 95% of the time in CS theory, like you'll really have like 2 sums, and if they're finite sums, like it's like sum I and some finite set s, and sum over j and some finite set t of blah of I and j, then you can always interchange them. And it's like just like this weird fact of like cosmic fact of reality that if you're like doing math and like somehow you encounter like a double sum, just immediately reverse it, interchange it, and like it'll make things better. Like I don't even know why. It's kind of a miracle. Actually, in some crazy way, that's exactly what happened here, right? If I may go back to this picture, it's gonna be hard because to draw on this picture, but like, the integral, the area under the curve is like, the normal way you do it is like this way, and you're like summing up all the heights of these like green vertical lines I'm drawing. And sort of the way we made progress was by like interchanging it and like summing it up like horizontally. But okay, that's never mind. Yeah, in general, okay, we need some rules if like there's either an infinite sum or an integral about like when you can interchange it. And like in calculus, there's this like question of like, again, if you have like a double integral, like when can you interchange it? And there's this like theorem called like Fubini's theorem. And like you have to like sweat in like some painful way to like check all its hypotheses and stuff. Let me say, like, for example, in like homework, like I'm not gonna like stress you about this. I mean, it's fine. Generally, if all of the sums involved are finite, even though they're infinite sums, like the typical case when everything is fine is when everything is non-negative and the sums are finite despite being like that, the actual value of the sum is finite despite being an infinite potential sum. This is when it's okay. I mean, if we were in this picture, for example, like we might actually have an integral and a sum going on, like somehow, like maybe like let me try to draw with big. We might try to draw with sorry. You know, here we have kind of like a sum and an integral. Like there's like this piece plus this piece plus this piece. So that's sort of like a sum of integrals, right? If you forget that this is like a flat thing, you didn't know it, and you just thought like, oh, I have to use calculus to compute the area under this rectangle. But now we have like a different piece and a different piece. It's like a sum of 3 integrals. And yeah, here, I guess what I'm saying is like in this case, I think you'll find that like everything is like very finite anyway. Like the things when you interchange, you'll have like an integral. Because I let you assume that x is only takes on finitely many values, like basically you're gonna have this feature that like things eventually stop. Like you know, you look at the maximum value of x and like nothing is going on beyond there, so you can forget about it. So like your integrals are like finite and like your sums only have finitely many pieces. So like this is definitely the case, and everything is non-negative. So like this is definitely the case where it's going to be okay.
Yeah, that makes sense.
Cool. Yeah, it's a good question though, because like, you know, I'm making you like sweat like some math things, like actively making you sweat some math things. And then maybe it's a little weird where I'm like, well, don't worry about this one, but yeah, this is the case. It is okay. And also, I don't know, I don't want to get into like, you know, weird like measure theory or super advanced calculus in this course. Okay. Any other like question? I was thinking of like going back to problem 2D, but if there's like another other question, or like can check that out too.
For 2.C, how to get the upper bound and the lower bound is the same constant C?
Oh, this one here.
Yes.
Sorry, yeah, this one, 2.3. Yeah, that's a good question. Yeah. Okay, so this one was about, we were doing Stirling's formula. And just to remind you, somehow you end up looking at like the logarithm function. It's like a terrible drawing. Okay, this is ln x. And like somehow Stirling's formula all boiled down to getting like an extremely like accurate. Okay, well actually you had to get this extremely accurate like sum of like these like rectangles, right? That was like literally Stirling's formula. It's like you exponentiate, but it's like basically about getting the exact area of these rectangles. And we're like, okay, like first pass, you could say it's like roughly the area under the curve up until this point. And then we were like, oh, but like, let's be more refined. It's like the area under the curve plus like the volume of these like curvy triangles. And so we had to like add up all these curvy triangles. And then we were like, oh, this is like approximately the area of like the flat triangle, which we could exactly add up. And so like the only remaining inaccuracy in our estimation was like the area of these like slivers that you get by like superimposing the straight and flat ones. So like for every, if we like super zoom in here, like for every one of these rectangles, we get this like sliver here. And like if we could figure out the area of all these slivers, if we could somehow figure out the area of all these slivers exactly, it's not a very informative drawing. if we could add up all these like sliver areas all the way up to the last one, just like this sliver plus this sliver plus this sliver, etc. Last sliver, then we would like exactly know n factorial, like with no problem. So we have some difficulty. Maybe we don't know the exact sum of the slivers from here to here. Or maybe we do we?
From the 2 B, we get is smaller than 1/8.
Yes, that's right. So the question has you show that, wait, what does the question have you show? So we have 1/8. Oh yeah. Oh, so wait, yeah, the question has you show something about like 1/8, but did you like draw a conclusion for that about the number 1/8?
Sorry, what is your question?
Okay, so yeah, so I guess the question had you show that like, okay, you show that like this first sliver has like area at most 1/8, it's like 1 minus a half or something.
Right.
And this one is like at most 1/8, a half minus a third. And then this one is like at most 1/8, a third minus a quarter, etc. So did you draw like a conclusion from this?
Yes, right.
What is the conclusion?
So we know the sum of all the silver is smaller than 1/8.
Yeah, now when you say all the slivers, which slivers do you mean?
From the first slivers to the nth slivers.
Okay, yeah, so first sliver to the nth sliver adds to at most 1/8 times, I guess like 1 minus 1/n, or maybe there could be a +1 here, I'm not sure, but something like this. Okay. Neat. So do you know the exact sum of the area of the slivers?
No.
Okay. Do you need to know the exact number of the area of the slivers to solve the problem?
I think no, but the constant is not enough, I think.
Sorry?
I think the constant here is not enough for we get the C is the same for both the upper bound and the lower bound.
Right. So you're saying like, okay, we have an upper bound on the, okay, so the area of the, okay, we have the upper bound on the area of slivers is 1/8, I guess. And the lower bound is 0. I mean, you could maybe work even harder to get like some lower bound, but yeah. So, and you're like sad that these are not equal, huh?
Yes, yes.
What if I told you, well, what if I, what if I told you is exactly 0.07359? Then could you solve the problem?
Yes.
Okay. What if I told you is exactly 0.09252? Then could you solve the problem?
What is this number mean?
It's a number I just made off of the top of my head, but like if I told you that was the exact sum of the area of the slivers, could you complete the problem?
Yes.
Okay.
Well, I think if we can get some low order term, it's okay. It's also enough, I think.
Yeah, actually, it's a good question. Suppose like well, yeah, this is a bit funny. Suppose like some extremely like brilliant, all-powerful person came down to you and said like, you know, I promise you this sum of the slivers is like 0.01 exactly. Would you have a question for that person? And but now you can like try to solve the problem, but you might have, can you solve the problem?
Sorry, I do not get it.
Okay, let's see. Okay, what is the problem actually? Remind me of the problem.
Oh, I just mean I do not get your last sentence. Can you repeat?
Oh, well, my last sentence was like, suppose somebody told you everything there is to know about the slivers.
Okay.
Could you solve the problem?
I think we need not an exact estimation for the slivers, but we need some lower bounds and upper bounds.
True. Yeah, I'm being like a little bit annoying here because like I don't want to just sort of exactly tell you, but like let's try it this way. I will answer any question you want about the slivers. Ask me anything about the slivers, I'll just tell you the true answer. But like you now have to use this ability, which I'm granting you for the next few minutes, to like solve the problem. So ask me anything. Anybody else in the call too? Like ask me anything about the slivers.
Well,
I'll give you some answers.
If you know exactly what they are, then you know exactly what ln of n factorial is, right?
Is that your question? I guess you'll
No,
give me a question.
I'm
Different answer
saying-
about question.
That's what I'm
Sorry,
saying. That's what I'm saying is the case, right? So that's what you could do.
Can you repeat that?
So the ln of n factorial is like the area of the rectangles plus the straight triangles minus the slivers. And
when you say the slivers, let me dive into that for a second. Which slivers?
The sum of all of them.
When you say all, what do you mean?
Like the 1 to n minus 1 where
yeah, okay, yeah.
K slivers. Yeah. Well, I'm just saying if you know exactly what the slivers are, then you know exactly what ln of n factorial is.
Yes, good. But okay, so in the problem, you don't have to exactly know. You're not actually even asked to like exactly get like a formula for n factorial. You're allowed some kind of error, right?
Yeah, so it's 1 over n. So that's why it was kind of confusing to me that we were ditching the 1/8 times 1 minus 1 over n. It seems like we should keep that around.
Maybe. Well, okay, so yeah, so actually, how accurately do you need to know the area of the slivers in order to solve the problem?
I'm not sure. I guess just up to this order 1 over n term.
Yeah, I think so. I mean, there's some like log in there. You have to like take some care, but like I think it does turn out to be like if you crunch the numbers, it's like you need to figure out the sum of these slivers, the light blue slivers inside this thing that I'm outlining here, up to like plus or minus order 1 over n, I think.
That might not be right, but yeah.
Yeah, I think it is right. But yeah, I agree that like we have to like try to like look into it for a few more seconds to nail it down. But I think that is right. So let's just hypothesize that that's right for now. So the question is, but the funny thing is like, okay, you yourself don't actually have to name the number, which is such that, okay, so we want like area of slivers up, between 1 and n. It's like a funny question. We need to like, okay, ideally we want to like be able to say like equals like some specific number, which I'll just call alpha for the lack of a better letter, plus or minus order 1 over n. The weird thing is we don't have to like literally explicitly name alpha. Like we don't have to be like, it's 0.06. Like we just have to show that there exists an alpha. So like, one could ask, how could that be wrong? Could there not be such an alpha? Like, for example, imagine I asked you to literally prove the opposite of the question. Prove that there does not exist a constant c such that n factorial blah, blah, blah equals c times whatever plus or minus order 1 over n.
Well, I guess the only way it could not be true is if the area of the slivers is like huge. Otherwise, you can express it as alpha times this order 1 over n term, right? No matter what.
Well, yeah, the thing we kind of know is, well, we have this area of the slivers. We know it's between 0 and 1/8, 1 minus 1 over n or something.
Yeah, so I guess you're just saying we need to be like a little more clever with the 0 side.
No, not really. Like what I'm saying is like, here's what could be the case. Perhaps the area of slivers up to n equals 100 is like 0.04-ish, but the area up to n equals 200 is like 0.12-ish, and like the area up to like n equals 300 is 0.02-ish. And then in this case, you wouldn't be able to say like, oh yeah, like there's one number alpha such that like this amount is like alpha plus or minus 1 over n. Like this information is all consistent with this because all these numbers are between 0.04, 0.12, 0.02. They're all between 0 and an 8. But like, is it really like this? In fact, there's like a clear reason why this is definite, like this weird example I've just written here in the arrow is like, obviously can't be what's going on.
Well, yeah, I mean, we have if n is 300, then we already have the 200 slivers.
Yeah, so for example, this could not be 0.02. It's obviously got to be more than 0.12. So maybe I'm like, okay, the area of the first n slivers is 0.13. Oh, well, that's not less than 0.1/8. So let me say 0.121. And then you might ask me, well, what's the area of the first 400 slivers? And I'd be like, it's 0.122. And then you might ask me, what's the area of the first 500 slivers? And I might be like, 0.1223. Like, what question would you ask me next? That's why I want to get in this like dialogue where like I'll answer any question you want about like the slivers area. So like ask me another one. I've just given you like 5 pieces of information.
Oh, I guess we could ask if it ever exceeds some value.
Okay, go ahead and ask.
I don't know. Okay, one sec.
Okay.
I only said that because the way you were suggesting the terms suggested it, but
I encourage you to literally ask me a literal question now to like follow up on this, these questions and answers. Try to pin me down.
Okay, so is it ever bigger than like 0.13?
Is it ever bigger than 1.13? Ever bigger than 0.13? No. Next question.
Okay, well, I mean, doesn't that just give us an immediate error bound since the only error was like with the 0, we're not counting the slivers at all, and with the other one, we are. Yeah, and so if we know that that error is at most 0.13, then I guess we're in good shape.
No, you have to get you have to like get the area of the slivers for a given n up to like plus or minus 1 over order 1 over n.
Oh yeah. So we're still not there.
One thing to notice here is like I definitely had to say no. I had to say no because you asked about 0.13 and 0.13 is bigger than 1/8.
Oh.
You already told me that you already showed that like basically for every n it's at most 1/8. So like I definitely had to say I definitely had to say no there. But ask me another one. Ask me a trickier one. How about somebody else who's on the call? How about, let's see, we got 5 people here. I'll pick one of y'all at random. Need a random number between 1 and 5. All right, RY. Oh, that's a good, those are some good initials. Do you have a question about the slivers?
I think I am kind of confused, but I guess based off of this,
You asked about 600.
I mean, okay, what would it be for like n equals 600?
For n equals 600, I'm telling you the area of the slivers is 0.12234. You're like pinning me down a little bit here. Ask me another one.
What is n equals 700?
Okay, 700, it's 0.1223449. This is like we got up to like this sliver, this sliver, this sliver, this sliver, this sliver, and like we've added it up from like 0 all the way to like 700.
Okay.
Okay.
So is this airbound something like the maximum minus something related to n, I guess?
You say maximum, what do you mean?
Oh, by the max, the upper bound that we found that was 1/8 times 1 minus 1 over n.
Yeah, you know that basically whatever you ask me, I'm gonna say a number that's 1/8. Ask me a really big one.
N equals 1,000.
Oh, you can do bigger than that.
N equals 10,000.
Sure. N equals 10,000. It's those add up. Wow, 10,000 is way out here. Those add up to 0.12234900562. Now ask me like the biggest one you can imagine.
Infinity. Like,
yeah. Okay. Now you're cooking. What is it for n equals infinity? First of all, does that question make sense? It kind of does, right?
Okay.
I mean, there's like infinitely many slivers, one for each natural number. And we do know that like, if you add them all up, it's still less than 1/8, right? It cannot be bigger than 1/8. If somehow like at some point, like at 1,640,000, it got bigger than 1/8, that would be impossible, right? Because we know even at like 1 billion, blah, 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 it's still at most 1/8 minus 1 over a billion. So indeed, like, it's possible, like you add up all these, literally all the slivers, and now I have to like, now I'm really, I have to tell you the kind of the answer, right? Like I might say like, oh, it's like, I don't know, it's like some number called, you know, it's obviously going to be like 0.12249000562, blah, blah, blah. I don't know, maybe it's finite, rational, maybe it's irrational. I don't know. It's some number, maybe some alpha. So that's some good information you got out of me there. So now you know if you add up all the slivers, it adds up to this specific number. Now you might dial it back and be like, oh, what about the first trillion slivers? That's a lot of slivers. Probably adds up to pretty close to this, right? In fact, if you add up the first trillion slivers, this is 1 trillion here. It's pretty close to all the slivers. I mean, well, in some sense, like all the slivers is this. Like the only stuff you failed to add up is like this. But like this is very small. This is what you or hope. Like you hope this is like super small. In fact, how small do you hope this is?
Order 1 over n. Right.
Yeah, very good. Exactly. Order 1 over n. So if this was over, obviously when n equals 1 trillion, yeah. Then if you could show that, life would be so great. So, okay, let's leave it there. I feel a little bad because we were going to come back to, I mean, patiently waiting so long for this, like, this one about Stirling's formula, and now it's like out of time. So for those patiently waiting, let me give you some like direct hints, because like, yeah, I don't want to like use up all your time here. So going all the way back to this problem. First of all, your thoughts about using the central binomial coefficients is like very good. So like focusing in on like n, which is n over 2. Like from Stirling, you know this is like exactly, well, it's very close to something. I think it's like root 2 over pi times 1 over root n. Or maybe there's like some, maybe it's something involving root 2s and pi's with Stirling. You can work that out. And that's exactly like this area. It's literally, if you, I don't know if you just saw what I did there. I like zoomed into the like the so-called discrete picture. And like, that's literally the height of, whoops, this bar here is like literally, well, it's extremely close to whatever this is, like 1 over root n times this, I don't know, root 2 over pi or something. And like these other bars are also probably pretty close to that height. Well, the one's really close to n over 2. And we want to compare that with like, here we have this problem that like, you know, Esseen helped us figure out the volume of, or the area of this like curvy trapezoid. And it was sort of related to 1 over root 2 pi, but that was like this thing. So I was actually trying to give you a hint before when I was like zooming in on it, like zoom, zoom, zoom. Like maybe what we should do is like, instead of going out to like 1 standard deviation, maybe we should go out to like 0.000, oh, it's a very large marker. We should go out to like 0.0001 standard deviations for a very small value of 0.001. And that's going to make some progress because, see, here, like the triangle you'll get if you study that instead of 1 standard deviation, or the rectangle you'll get, this is like much more similar to the area under the curve from here to here. Like the area under the curve, okay, it's like it's a trapezoid with like a slightly curvy side, but this is going to be like much closer to 1 over root 2 pi times point, what did I say? 0.0001. That's going to be much closer. So on one hand, okay, Barry Esseen will tell you that like this area, well, it'll tell you that like maybe if you go to like 0.01 standard deviations, 0.001 standard deviations here, it's very close to the area under the green curve, just like here. But like since 0.001 is so small, like that's really close to the area of this like yellow rectangle, which we know is exactly 1 over root 2 pi times this 0.001. So maybe if we pursue that line of inquiry, we might need to make 0.001 even smaller. We can like, try to get like a link between like the height of this bar, which we kind of exactly know due to Stirling, and the area of this green almost rectangle, and therefore the area of this yellow rectangle, which also has like a root 2 pi in it. So thanks for waiting. That's my bunch of hints for that problem. Okay, these are all great questions. Any other like quick questions, even though it's like a little bit over time? Okay, well, thanks for all for coming. I'll see you tomorrow in class.
Thank you.